Hello, everyone. My name is Matthias. I'm CTO and co-founder of Liquid AI. And today I want to show you how to fine-tune a liquid foundation model, which is a language model that we trained on purely AMD hardware. So there's this misconception about NVIDIA that, hey, NVIDIA is the go-to hardware provider for training with PyTorch. So the only thing that's really supported with PyTorch. And maybe other hardware providers are good for inference and so on, like AMD can be used for inference. And I want to show you that this has been maybe the case in the past, but today with the latest ROCm stack, not the case anymore. And we can fully fine-tune a model without needing any NVIDIA hardware. So let's get started on this. And I want to show you and walk you through the entire process, end to end anyway. So first one, actually, I want to connect you to the hardware that we are talking about. And this was provided by us thanks to TensorWave, which is a cloud, neo cloud provider in a way, specifically for AMD GPU hardware, which is like they're doing a great job of providing and making the access as easy and smooth as possible. So yeah, great working with them. So on the NVIDIA, everybody knows like NVIDIA SMI, kind of the standard in a way tool, CLI in a way to just query what hardware, what device, what type of GPU we actually have and the status of the GPU. And the same thing exists in the AMD ecosystem, but it's called AMD SMI. So if you run AMD SMI, we'll see output looks very similar to like how we look at NVIDIA SMI. However, we see that actually here we have an AMD Instinct MI325X hardware. Which is quite nice, and we have 8 of them in total. And there's like not really much that like maybe dummy process that actually uses these GPUs. And one thing that is really nice with AMD, that is just I think the key factor here is like if you look at the memory that we have. So this thing has 262 gigabytes of HBM memory. So this is a massive amount of memory that we have per device in a way. And this allows really like fitting massive models on one GPU without needing sharding or having massive batch sizes that really brings up in a way the flop and total utilization of that. So as I mentioned before, I want to walk you through end to end. So this is basically like a plain hardware that we get access to. And this has ROCm, you see here, ROCm 7.1.1 installed there. So again, like AMD did a great job in the latest ROCm 7 version in a way by really like making sure the PyTorch and everything works really like smoothly out of the box in a way. And this ROCm latest as an equivalent basically of CUDA has been installed in a way on the system in a way. But that's it. There's no Python or anything like that in there. So I want to walk you through this. So let's get started in a way and let's create a directory tune basically and go into this tune. One thing that is I want to show you that I already installed UV, which is like the package manager, which is similar to pip, but it's made with Rust and it's much faster basically than pip, but overall like very similar. And one thing that we do first is like basically creating a virtual environment, and this can be done with UV-venv, and then we can source it basically similar to like how we would do it with a pip. Next up, we need actually like to install PyTorch. So again, because this is just plain Python environment basically here. And we see like the latest stable 2.10 version of PyTorch in a way with Linux. Python has also a ROCm backend in a way already shipped with like standard. So upstream mainline in a way we have a ROCm version of that, which is also again very nice. And we can just pip install it, but instead of just pip, we say UV pip install. The rest is very similar in a way there. And so now this will install in a way all the dependencies with like the ROCm backend. So this will take a while. So even though like UV is much faster than pip, still takes a while. So let's let it install in a way in the background a bit. Another thing that is important is just, PyTorch is like one thing, but we need actually like also transformers, like Hugging Face transformer library and like some fine-tuning libraries on top, like Accelerate, which makes use of easy data parallelism, and also a TRL, which is like transformer from Hugging Face transformer reinforcement learning library. So let's go to docs.liquid.ai in a way. And here we have on the left panel also here TRL fine-tuning in a way. And it's specifically the dependency that we need TRL transformers. Torch we already have. PEFT we don't need. We do full fine-tuning here in this example. And also Accelerate, which is really nice for data parallel fine-tuning. So again, UV pip installed this stuff. Takes a while in a way, but then it should be everything setup. In the meanwhile, we can quickly go through the script in a way that I've prepared for the fine-tuning. So this is based on, like, if you go on the left page, we have here in the Liquid AI docs some documentation on, like, basically doing full fine-tuning, and then full fine-tuning and PEFT, which is like LoRa fine-tuning. And I basically took that example in a way with like small and minor modifications that I want to go through. Specifically on top of that, I just get the local rank and print in a way the number of GPUs here in a way. This is just that I really want to show you that, hey, we are actually running on AMD. So even though we say like torch.CUDA, but if you say .device name, you will actually see it's AMD, which is kind of funny. But yeah, so much about that. And because we want to do data parallel, so we, as we seen before in the AMD SMI, we have actually 8 GPUs, and we want to do data parallel. Basically just creating replica of the model, each of them seeing only a subset of this data set, and basically synchronizing the gradients in a way, which is a standard way to kind of accelerate the training if you have more than one GPU. But this means that this basically program is executed by 8 different processes, and so that's why, in order to not spam, the standard out with like a lot of print statements, I just want to make sure that we only print like if you rank 0. Then we have like standard stuff in a way where we just instantiate the LFM 2.51b instruct, 1.2b instruct model with the tokenizer in a way. One minor modification I did here is like that I instantiate with float 32 in a way, which is a bit more stable with fine tuning and so on. And as I mentioned before, we have so much memory on AMD that we don't really care about that too much. For dataset, I'm using like this dummy dataset shell helper. I'm gonna go through is like a Hugging Face my username. You will see that it's a kind of a standard dummy dataset. Basically, like just with field messages, and then like a standard chatML template where basically you have like a instruction by a user, and then basically the model answers with like some text and like a markdown environment with like some command in a way. It's not kind of a fancy data set. It's just more like for demo use case. Finally, we have like our SFT config here, and a couple of parameters, like basically the standard thing, like we train here in this example, 3 epochs, 32 batch size in a way with like 2e-5 as a learning rate. We log every 100 steps. Gradient / activation checkpointing is just making the bit more memory efficient and so on. Shouldn't affect actually in this setting too much. And for data loader also that we don't have in the Liquid AI docs, but we have in this example here, basically just that we don't starve the GPU, because these are very powerful GPUs. So we actually want to spawn like 4 different processes kind of that fetch the data, prepare them, and already kind of make them ready for the GPU to just consume them quickly in a way. Finally, we instantiate the SFT trainer, which just configs the model and so on, we train it, and then we save it. And at the end, again, like only on rank 1, rank 0, we just basically instantiate the model again, load it from the memory, and then we just have a while true loop, so an endless loop, where we just ask the user for prompt. So you input a prompt, and then basically it applies the chat template and finally generate. So it basically just has a loop where you chat with the model, single turn, and reset the conversation every step, just as a debugging or testing scenarios at the end. So very simple fine-tuning script in a way, yeah. In the meanwhile, we'll see here that everything has been already installed. Then we can basically copy over that file onto this machine. And in the simplest case, we could just run Python 3 FT, basically the fine-tuning script. There's one issue in a way, and this is that if we execute it like that, it will not use the the transformers like accelerate package that we installed in a way there for the data parallelism. But instead, what it will do now is basically just using the 8 GPUs not as a data parallel process, but kind of shard the model across the 8 GPUs by putting like different tensors on different GPUs and so on, which is kind of the auto setting in transformers. And yeah, so that script should start if you connect to the node again and run the AMD SMI. We'll see, okay, script hasn't really started yet. So yeah, basically like, yeah, we see here that it basically prints this 8 GPUs. So when you say like the funny thing that I mentioned before, like CUDA.device name, is AMD, which is nice. And then basically just prints out a couple of stuff like ROCm, which is kind of the communication library in a way between different GPUs. This is more relevant actually for multi-node training. So this is all here single node training, but for multi-node training, actually there's like more stuff necessary to make sure that the different nodes, compute nodes, when you scale out, communicate with each other in a nice way. So this should be already training, and you see actually it's very slow. So it's like 40 seconds per iteration and so on, like it's massively slow. And if you look at, for instance, the GPU utilization, with again running AMD SMI on that screen, we see that we have like 8%, 0%, this is very slow. And because this is actually not data parallel, this is actually just kind of model parallel. Like if you think about it, it's sharded, and it's a very small model, so there's like a lot of communication between the GPUs that are absolutely not necessary. And it consumes very little memory in a way. So in a way to really run this like with data parallel, we need not to execute it with Python 3, but accelerate launch, which again like will in a minute or in a short second print out the information that it actually spawns 8 processes, where each of the processes has a replica, and like they communicate only with the gradient. So there's no like for each tensor to kind of communicate with each other, but only like with the gradient update. So the communication between GPUs is much more reduced. Again, like prints here the information. The default setting is like data parallel with like 8 non-processes. We don't use any mixed precision or so, or also no torch grad autocompile and so on for now. This can be optimized, I think, later on. This is here just an example in a way there. And we instantiate the model 8 times, basically replicas of the model. And they only stay in sync by basically making sure that the gradient updates are synchronized. So one thing that we see here is like already like we don't have 40 seconds per iterations, but actually 2+ iterations per second. So this actually trains quite fast. And like, yeah, overall the entire training process will take roughly like 15 minutes or so. And again, if you go into that tab and execute the AMD SMI, you'll see that the GPU utilization here is like almost 100%. So this is much, much better now. It also consumes a bit more memory in a way, obviously, because like stuff is replicated now than sharded. Previously was sharded. But still like 17%, which is like really impressive given that there's way more room to kind of fit on this kind of massive accelerators. Yeah, here just the processes again, like because we use in the other tab we set like the number workers for the data loader to 4 in a way. So each process for each GPU in a way has already like multiple worker processes to just fetch and prepare the data patch, such that in a way we can feed it into the GPU very quickly. So yeah, so that's basically it in a way. Like this is just now training. It will, as we defined in our SFT config, every 100 steps log stuff like number of tokens trained, loss, learning rate, epoch, the token accuracy, and those kind of things. And in total, like, here almost like still like 13 minutes to go in a way for the full training in a way. And yeah, that's basically it. Like afterwards, as we defined in the script, it will just save in a way the model and the tokenizer into the lab, into this folder anyway, fully trained in a way where we can just unload it and use it for deployment or whatever we want to do then on top of it in a way. So yeah, let me run this a bit longer in a way and then show you in a way how the result will look like. But basically, like as it concerns for the training, that's it basically. Just like UV, pip install ROCm backed PyTorch, Hugging Face, accelerate, transformers, and that's it in a way. Just making sure that we have the right sharding strategy, that we don't accidentally use like a sharded version, like where we have like one process like with sharded tensor, but we actually do data parallel and so on. So this is just important in a way when we debug and see actually why it's slow in a way. But like this is actually like decent speed, and again, like as in the AMD SMI, we show the GPU utilization seems to be also quite acceptable for this training run here. All right, so yeah, let's now then wait until basically we went through the entire like training process with like the 3 epochs in a way. Currently, it's like 60% of the first epoch, as we see here. Yeah. So training has now completed, and we see that during the training, the loss has decreased a lot, like from 1.2 to around 0.4 or something. And also like conversely, the mean token accuracy from 71.9% at the beginning of training to kind of 88% at the end of training. So we probably here already like in a bit of an overfitting regime. But as I mentioned before, this is just an example task, an example data set to illustrate here that we can train on AMD hardware. And if you go back to the fine-tuning script, you see that after the training, we enter kind of this loop here where we instantiate the model and are in a loop where we can just read from the standard input, a prompt, and then apply chat template and generate up to 256 tokens. And I here entered for already, for instance, the prompt of like convert MP4 to MP3, and the model outputs like, hey, you can use FFmpeg to convert blah, blah, and using this kind of command here in a way that's kind of correct in some sense. Also, you can ask UV how to create a new environment. Let's see if this also UV init. Is this correct? Okay, it seems to be working. So also model doesn't lie in this for a second prompt, which is nice. And yeah, that's basically it. Like, so what we have shown here, basically like that we have a simple fine-tuning script in a way that just instances the model, loads an example data set, fine-tunes it with data parallel using the Hugging Face accelerate library, and then saves it as a kind of normal checkpoint, which is nice. So this has been done really end-to-end without a single NVIDIA GPU required in a way. The full training was done on AMD hardware with a ROCm stack. So PyTorch with the ROCm backend, plus TRL transformers, Hugging Face transformers, and the accelerate library in a way to kind of achieve a data parallel training of liquid LFM 2.5 1.2b instruct model. Maybe I forgot to mention a bit more on that LFM model in a way. This is trained by us. Like we developed this model specifically for on-device. So this model runs on a phone and runs locally with only like 1.2 billion parameters, which makes it like very small and efficient and maybe limited in terms of capability, just because of the scaling laws are counteracting kind of the capability. There's only so much capacity that we can really express like in 1.2 billion parameters. Therefore, usually like models like that need fine-tuning to kind of adapt to the domain or their tasks. In this simple scenario here, this shell helper that just gets like binary and like how to use that binary with what arguments and so on. The data set that we have here in a way, like how do you use like git TUI client, whatever, lazy git, and those kind of things, just to kind of adapt that small model to that domain. And yeah, that concludes this video. So thanks everyone for watching. Like if you have any feedback regarding this tutorial, regarding liquid foundation models and our docs, please reach out to us. Also, like there's much more releases coming from our side in the next weeks and months. So this is also very exciting to see. And yeah, do not hesitate to reach out